This is part 6 of the series Transformations, and in this part we're going to begin by looking at a summary of the postulates and theorems that we've come up with that relate to transformations. Now the first one that we're going to deal with is the translation postulate. The translation postulate said that a translation is a rigid motion, and you should also know that a rigid motion is known as an isometry. The next one we came up with was the reflection postulate. That said a reflection is a rigid motion. And then there was the rotation postulate, and that said a rotation is a rigid motion. Nothing new and surprising here. All these, translation, reflection, rotation, we said at first, when we first introduced this series, that these three were going to be transformations that preserve angle and length. Then we had the composition theorem. The composition theorem said a composition of two or more rigid motions results in a rigid motion. After that, we come to a new topic. And all of these transformations that we've looked at, translation, reflection, and rotation, and compositions of those transformations, are known as congruence transformations. So a congruence transformation is simply a rigid motion. All of these are rigid motions. The composition of rigid motions is a rigid motion. So all of these are congruence transformations. Now that brings us to the idea of what are congruent figures. We've looked at segment congruence and things of that nature. Jumping to the formal definition of congruent figures, two figures are congruent if there exists a rigid motion or composition of rigid motions that maps one figure onto the other. The implication here is that congruent figures have the same shape and the same size. So that's congruent figures. The next idea we're going to look at is a theorem that addresses the relationship of some compositions of reflections and translations. So let's take a look at that theorem at this point. This theorem is called the reflections in parallel lines theorem, and it states if a figure is reflected in two parallel lines, then the composite reflection is equivalent to a translation of the figure a distance equal to twice the separation of the parallel lines. So here we have our pre-image and our final image. And what we've done is reflected this image across this line to here, and then this figure is reflected across this line to here. And we're saying that the distance of movement of point A to point A prime, this distance in here, let's see if we can represent this. So this distance from here to here is twice the separation distance, this x distance between lines L and line M. So that's what this theorem says, that this double reflection, once here and then here, is equivalent to a translation equal to twice the distance of the separation of the two parallel lines across which you've reflected. Now the proof of this is kind of interesting, so that's what we're going to spend the rest of this part with. We're going to look at the proof of this. Now the situation for this proof, we're going to use just one point. And we're going to take point A, reflect it across line L to A prime, reflect it across line M to A double prime. And we're going to prove that the distance from A to A double prime, this distance, is equal to 2 times the distance of BC, which is this value x. And the idea behind the proof is using the segment addition postulate, because we know BC is made up of A prime B and A prime C, and A double prime is made up of 4 segments. This one, this one, this one, and this one. And because the nature of a translation or a reflection in a line is that this segment and this segment are equal, this segment and this segment are equal. So we'll have some cancellation opportunities there. So that's the idea. First thing we're going to do is write in our givens and move on from there. So here's a restatement of our given. Now to begin with, I want to use the fact that in the definition of a reflection, segment AB is congruent to A prime B, and segment A prime C is congruent to segment A double prime C. So that's the first thing I'm going to take advantage of. So that's our next statement. We're going to write that right here. So here we've stated AB is congruent to A prime B, A prime C is congruent to A double prime C. Now, this we can use the definition of congruent segments and say that the length of AB equals the length of A prime B, and the length of A prime C equals the length of A double prime C. So let's write that statement. Now our primary goal here is to relate A double prime, that whole segment, with 2 times BC. So the best way to approach is to write down A double prime and all of its constituent elements. So we're going to break down A double prime using the segment addition postulate and determine where that brings us. So that's our next statement. Now again, we want to relate A double prime to terms that include BC. Well, BC is made up of A double prime, or A prime B, and A prime C. So here we have an A prime B, and we know from this statement that AB is equal to A prime B. So I'm going to do a substitution of this into here, and we know that A double prime C is equal to A prime C. So I'm going to do that substitution down here. So I'm going to substitute this for this down here. So that's our next statement, to get us all in terms of segments of segment BC. Now here we have A double prime, all in terms of segments A prime B and A prime C that make up BC. And as we can see, there's A prime B and A prime B, so there's 2 of these and 2 of these. So we can simplify this expression by saying that A double prime equals 2 A prime B plus 2 A prime C. That's going to be our next statement. At this point, hopefully you can see we're getting close, because now we have a common 2 inside here, so we can use the distributive property to pull out that 2, and we'll have 2 times A prime B plus A prime C. And A prime B plus A prime C is simply BC. So we're only a couple of statements away from what we're actually trying to prove. So our next statement is going to be that distributive property idea. At this point, that's all we need to do is to define what BC is, what segment BC is in terms of A prime B and A prime C, and then do a substitution, and we've got our proof. So we're going to define BC using the segment addition postulate. That's going to go here. Finally, since we can see that BC is the equivalent of this expression here, we can do a substitution of BC for this expression here, and we'll have our final proof statement. So that's our last thing, is using the substitution property of equality. And here's our substitution. A double prime equals 2 BC. So the distance from A to A double prime, this double reflection, is equal to 2 times the distance from B to C, or the distance between line L and line M. That's the proof of the reflections in parallel lines theorem, or one of the proofs for that. Now let's look at another theorem that relates reflections in intersecting lines, and it involves a rotation. The reflections in intersecting lines theorem states, if a figure is reflected in 2 intersecting lines, then the resulting composition is equivalent to a rotation of the points of the figure about the point of intersection of the 2 lines of reflection through an angle whose measure is equal to twice the measure of the angle of separation of the lines of reflection. Lots of words, but it's a really simple theorem. here we have two lines that intersect. The angle of intersection, the angle of separation of the intersecting lines, is this angle here, x. What we're saying is if we take this figure, ABC, and reflect it across this first line, and then reflect that image across the second intersecting line, that double reflection from here to here and from here to here is equivalent to a rotation of all these points about this point P, which is the point of intersection of the two intersecting lines, through an angle, and that angle is going to be twice the angle of separation of the two lines. That's all it's saying. So if this angle of separation were 15 degrees, then this angle would be 30 degrees. If this angle were 30 degrees, this angle would be 60 degrees. And so that's all there is to the theorem. And we're going to be identifying what the equivalent rotations are. If we have a rotation, what's the separation of the intersecting lines? That's really all we're going to be concerned with at this point. Now, unfortunately, the proof of this theorem requires some ideas that we haven't yet gotten to. So we're going to have to defer the proof of this until a later chapter. But the idea is relatively simple. So let's not concern ourselves with the proof yet, and we'll look at it at some other time. Let us, however, go ahead and look at a few examples of these two theorems that we've just done. The reflections in parallel lines and reflections in intersecting lines theorems. So let's look at the first example. In this example, we know that segment AB is being reflected across line P and then reflected across line Q. P and Q are parallel, and we want to determine what we know from this picture. So first thing I'm going to do is draw in the segment A double prime, and I'm going to label this intersection point R and this one S. First thing we know, definition of a reflection, is that AR is congruent to A prime R. And we know that A prime S is congruent to A double prime S. So those are the first couple of things that we know. So we know that AR is congruent to A prime R and A prime S is congruent to A double prime S. We also know that the distance from A to A double prime is 2 times this distance, and that also means that B double prime is twice this distance. That's just a recap of the reflections in parallel lines theorem. So let's go ahead and look at another example. In this example, triangle ABC is reflected across line P and then across line Q. We want to find the distance between lines P and Q if the distance C to C double prime is 7.6. The theorem states that a double reflection is equivalent to a translation equal to twice the separation of the lines. Well, if the translation distance is 7.6, then the distance between the lines must be 3.8. So our distance here is 3.8. Now let's work another example. In this problem, segment AB is being reflected across R and then across S. We're told that lines R and S intersect at an angle of 23 degrees. So this angle is 23 degrees. We want to find the equivalent rotation. So we know that a double reflection is equivalent to a rotation equal to twice the angle of rotation. So this angle has to be 46 degrees. So the answer to the question is that the equivalent transformation is a rotation about point P of 46 degrees. And that pretty much wraps up the two theorems. And in the next part, we're going to start dilations. So I will talk to you in the next part.